Now, I don't think you can see what I'm talking about here, but I have a toolbar, taskbar, whatever you call it, that's covering part of the bottom of my screen, so I'm going to move it down out of the way. If you ever listen to the YouTube videos, you'll see these things in the way, and so that's what the deal is with them. Um, Also, we'll have one when I go to the whiteboard, so we'll pick up that when we get there. So if there are any questions, concerns, problems, issues whatsoever, please let me know now. Otherwise, we'll go on and get started where we left off last time. Anything from anybody? Let me just check and see if we have any others come in. Nope, we've still got 5. Okay. So silence, I guess, means consent. So let's move on. We're in chapter 12. We just got started in 12.1 last time, almost through with 12.1, and we'll be moving along through chapter 12. We're at the top of page 312, and they show here a couple of representative atoms. Okay, and why I say that, and I think I'll go to the whiteboard to show you kind of what I'm meaning there. Now, I'll tell you now, my drawing stinks and it's not going to be very pretty. Hopefully it won't be so distracting as to be harmful. Okay, also going to move the whiteboard a little bit to the left and up so that we can make maximum use of what whiteboard we have here. All right, now here is examples of 2 atoms. Okay, the first being hydrogen, the simplest atom in existence. Okay, it has 1 proton in the nucleus. Now that's not a very pretty proton, but I'm going to put a plus charge in it to indicate that's a proton. Now you may not be able to see it, that just looks like glob in the middle, but that's supposed to be a plus sign. That's a proton. All by itself. Most hydrogen, that's all there is. Flying around it, and this is in your book, and this is really going to be miserable, I'm sure. And I'm just drawing one potential path for it, and it's not anywhere that wiggly. Whoops, and it should come to a thing. That would be where a tiny, tiny, tiny little electron is, and that has a negative charge. I put a negative charge through there, you're not even going to be able to see it. That's all there is to a hydrogen atom. 1 proton in the middle, the nucleus, that's it. And that's a very dense nucleus, okay? That's where just about the entire mass of this hydrogen atom lives, okay? The slide that was up there before on the previous page in your text, page 311, shows that a proton is between 1,000 and 10,000 times heavier than, more massive than an electron is. So just about the entire mass is right here, okay? However, the volume of this hydrogen atom is defined by the path of that electron. So most of what's in this hydrogen atom is empty space, okay? Now, that electron is not just going through one circle there. It's somewhere, anywhere in a sphere, and not even a perfect sphere, sort of a spherical shape around that proton. It could be here, there, or there, anywhere, and it's moving very rapidly. And if you ever determine where it was, you wouldn't be able to determine what it was. There's a physics fact about that called the Heisenberg uncertainty principle. If you ever were able to determine the location, you wouldn't be able to determine its speed. If you could determine its speed, you'd have no clue where its location was. So it is an incredibly tiny little piece of matter, and that's about all it is. Hardly any mass and no discernible volume, okay, that it's taking, but it's flying around in what determines the volume of this hydrogen atom. Now that's hydrogen. Now here's another fairly simple atom, and that's carbon. Okay, now carbon, okay, um, it has 6 protons, 6 neutrons. Remember, neutrons are neutral, and they are packed into that tiny little nucleus. And I can't draw all of them. That would be far more than I could do. Let's just say that these are the 6 little protons interspersed with 6. I say little, they're more massive than electrons for sure. That's 1, 2, 3, 4, 5, 6, 7. Now these can be behind each other, around each other. I'm just drawing them here just to indicate I can't even count how many. Doesn't matter. There's 12 little objects there. 6 of them are positively charged. Those would be the protons. 6 of them are neutrally charged. That would be the neutrons. In other words, they have no charge. And they're interspersed somewhere in there behind each other and around each other. There's 1, 2, 3, 4, 5. I'll put one more here. And then there's supposed to be 6 more neutrons with no charge on them. Okay. Now, flying around these, you have 2 little electrons. And when I say little, I mean little. Okay. Electrons. Now, these are probably way too close. That would be one path, and this would be another path. Okay. And these both represent paths of tiny, incredibly tiny little electrons, both of which are negatively charged. And they're so tiny, when I draw the minus sign, it just completely obliterates anything. Those are what we call the inner shell electrons. They are on the same order of this, but since I drew that one way too big, so shrink that down, and that's what you've got here. Okay, then that's 2. Because there's 6 protons, it needs 4 more, and the 4 more electrons are floating around somewhere out here. Okay, 1, 2, 3, if I could get this, 4, and these are your outer shell electrons. Now you don't need to know too much about inner and outer shells, but just know they exist. These electrons are floating around out here. Each one of them is a tiny little bit of matter that is much, much, much smaller than the, incredibly much smaller than the protons and neutrons. Like I said, between 1,000th and 1/10,000th of the mass of a proton or an electron or a neutron, and their volume is almost indiscernible. No one's been able to determine how big an electron actually is. They're incredibly, incredibly tiny. Okay, but they carry a negative charge. So every one of these is a little negative charge. That big old neutron in there has no charge whatsoever. Big old proton has a single positive charge, but these tiny, 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 tiny little electrons have a whole negative charge. Okay, so you have a total of 6. 2 in the inner shell, 4 in the outer shell. Now the outer shell loves to have 8, and that's why carbon is so reactive with so many things. It's going to be sharing electrons with other things, like oxygen, like hydrogen. Like this one hydrogen could share with one of these here, and now that shell has 2, and this one has 2, and hydrogen wants 2 in its outer shell. So that's what they do. They share electrons. You don't need to know all of that, but just to give you an idea. Now again, this is not at all to scale. That nucleus is so incredibly tiny you can't imagine it, but it is incredibly massive, okay? Because all the mass is pretty much located in that tiny, tiny, tiny little nucleus, and then these electrons are out here flying all around, and they determine the atom's volume. They have almost no volume themselves, but they determine the volume by flying around, and that determines the sort of the boundary of that carbon atom. Now those are 2 very, very small atoms. Okay, the hydrogen is in the first shell and first level of your periodic table, and carbon's in the second level. Okay, you have five more rows, a total of 7 rows in your periodic table, and many of those rows have um, all but the first row only has 2. The next row has 6 or 8, and then the next row is same, and then the next one has another. Um, Goodness gracious, I'm going blank on how many. Something like another 10 more, and then the bottom rows have even 14 more. So I mean, you just have enormous atoms that you couldn't even draw here. It would just be, I couldn't draw obviously. Okay, but anyway, that's what makes up matter. Okay, protons, electrons, neutrons. There are approximately 100 known atoms or chemical elements. Remember, we talked about that before. Atom is the microscopic concept of a single indivisible particle that represents a single bit of matter, like carbon or hydrogen or whatever. The smallest it can be and still be carbon or hydrogen or whatever. Whereas an element is a macroscopic concept that's all made up of the same atoms. Okay. Now, they mention here a name. Ernest Rutherford developed the concept of the atomic nucleus, which is what I was trying to describe in that center there. Okay, he did it by a very ingenious experiment, but we don't have time to go into that. Now, matter exists in 3 states. Now, a lot of books don't use that term states anymore. They use phases. And I'll tend to use phases because now that quantum mechanics, which Rutherford was part of, is in existence, state means something else in physics. State means a energy level. Okay, so to keep from confusing that, I usually use phases: solid phase, liquid phase, and gas phase. And you probably have a pretty good idea of what each of those are. Just look around you. Most of the things you see are solids. Okay, the trees, the building, the window, the glass, the wood, the plaster, the clothes hamper, the desk. All these things are solids. They have definite volumes and definite shapes. Okay, now if I looked out, I see our dog's tub that she likes to get in. She's a golden retriever. I also see a bird bath, and I can see in that is liquid because I think there's still a little bit of rain falling. I can see little splatters there. That's what a liquid is. A liquid also has definite volume, but indefinite shape. It takes the shape of its container. The liquid out there in the bird bath is a different shape than the liquid that's in the dog's tub, but they're both the same liquid, water. It takes whatever the shape of the container. And a gas, on the other hand, it's everything that I don't see out there between me and the trees and the buildings and everything else out there is filled with gas. Now, some gases you can see because they're colored. The ones I'm looking through are all clear gases, mostly nitrogen. About 78 to 80% of what I'm looking through is nitrogen. I couldn't tell nitrogen from a hole in the road because you can't see it. About 18 to 20% of that would be oxygen. Those two make up just about all of our atmosphere. But there's some carbon dioxide out there. There's some water vapor out there. Certainly today the humidity was quite high, but still this is a very small amount of water vapor. There's probably a little bit of ammonia there. There's probably a little bit of hydrogen sulfide there. There's lots of other gases mixed in there. None of them have any discernible color or anything else about them, but those are gases. They have no definite volume. They'll take whatever the shape of the container and fill the entire volume of the container. Now, if we were all in one classroom, like I'm used to teaching this class, if we were all in one classroom and I were to sneak into the classroom before class and then sometime during class open up a bottle of ammonia and then say, well, I need to go to the office for a minute, y'all just wait. The people sitting closest to the front of the room would start smelling that ammonia, and soon the people in the back's eyes would be burning and tearing up and stuff, and I would finally come back in and I would be tearing up, and because the ammonia gas is escaping from the volume and filling the whole room. Now, it takes a while to get there, but it will ultimately get there. That's a gas. Has no definite shape, no definite volume. It'll fill, even though very few molecules, fill the whole volume, no matter how big a room it's in. It might take a while, but it will do it. Those are the difference in those three phases of matter. Okay. Now, let's go back to the slide. We still have the 5 people here and me. There's our slide again. Now, this is the one that showed, and let's go from current slide. This shows the masses of those 3 subparticles, atomic particles that make up an atom. Protons and neutrons, almost the same mass. Neutrons are slightly bigger. Electrons, look at that exponent. 4 fewer than these exponents. So that's between 1,000 and 10,000th the size, the mass of either a proton or a neutron. The diameter, these are very small, but indiscernible for an electron. They have never been able to figure out how big an electron is. Okay. However, the charges, same charge in that big old proton than there is in that tiny little electron. Absolutely no charge in the neutron. Okay, we've been there, done that. Here's a slide we were referring to. This represents a solid. Now, what this is trying to show you here is that you have 2 different types of atoms here. This atom is connected to, the blue atoms are connected to the white atoms, okay? And the blue atoms look like they have a maximum of 4 connection points. Those could be carbon, okay, because carbon had those 4 free electrons in the outer shell, okay? Now, not everyone is connected 4 times, but most of them are. More than likely there's another connection up here you don't see, or down there you don't see. This may have 2, or else that's a double connection there or here. Whatever. That's a solid. Those atoms in a solid are fixed in position. What we call it is a crystal structure, a crystal lattice. Now, what you may notice, now this isn't characteristic of carbon, but it could be, the way they've drawn this, the carbons are only connected to others, because you don't ever see a blue connected to another blue. Now, carbon quite often will connect to another carbon, so therefore this may not be carbon. In fact, I don't know what it could be. But the others are only connected to the carbon as well. You don't see the white ones connected to another white one. And what that means is this fixed crystal lattice is here, and it's 3-dimensional, so that's why it looks sort of random here. It's not random. They're fixed in positions. And therefore the solid has its own shape and its own volume. That's what makes a solid a solid. However, the liquid molecules are free to move around, but they stay in close proximity to each other. That's what gives them a definite volume, but they take the shape of whatever container they're in. The atoms, and I'll extend that, the molecules of the liquid stay pretty close to each other. They have that attraction, they call it cohesion, but they do not stay in a fixed lattice like the solid does. But once they become a gas, now the atoms are absolutely free to go anywhere they want to. I'll make that molecules as well. Sometimes those molecules will collide, but when they do, they don't stick together. They bounce off elastically, resuming their path by themselves. Now, this is showing 2 collisions here and 3 not collisions. Usually there'll be a lot more not collisions and very few collisions. And when there are collisions, they just bounce right off each other and head on their merry way. Not so with liquids. They stay really close to each other. That's why they have a definite volume. Gases do not. They fly anywhere. Now, there is actually a fourth phase of matter, but you don't need to know it, but just to fill out your resume here. How do you get a solid to become a liquid? What would you suggest? If you had a solid material, how would you get it to become a liquid? Give me a guess. For instance, I go down to my freezer and I pull out a cube of ice. That's a solid, has a fixed crystal structure. It's a solid, has a fixed volume, a fixed shape. How do I change that to a liquid? Pretty simple, isn't it? How? I see Jalen's trying to say something, but I can't hear you. Is your microphone working? It just turned off. Now it's back on. Can you say something? Haven't been able to hear you yet. Let me check anybody else. Somebody else say something. Okay, Macy's trying to say something. I cannot hear Macy. So have I lost contact? Let me see. Earlier today, one time, my button. Okay. All right. I can't see anybody either. Can someone turn on your camera as well? Okay. Can you hear me, Jalen? Yes or no? You can hear me. Say something, Jalen. Anything. Okay. I cannot hear you. Okay. Will someone else? Okay. Macy's going to try to say something. Say something, Macy. Jalen, can you hear Macy? Yes or no? You can hear Macy. I cannot. What is wrong with my picture here? Okay. I thought y'all were just being very quiet, but evidently it's something more than that. I think what I'm going to have to do is, see, I can see. Okay, let me. Okay, you can hear me now. Yes or no? Yeah. Okay. Um, I thought this was supposed to change the. Oh, there it is. Improving volume any? No? Now I can hear you. Someone said something. Macy, was that you? Okay. To my button here, and I. Now can you hear me? Okay, and I can hear you. Okay. So evidently my volume twisted down. I don't know why. Okay. Now, I don't even remember my question. Oh yeah. Yes. How do you do that? Yes, you heat it up. You add energy to it. And you see those now here's what those little red lines are indicating. It's indicating those molecules, even in the crystal structure, are always vibrating. They're never still. They're always vibrating. Okay? But that's all they can do is vibrate. Okay? But you add more heat to them and they vibrate faster and faster, and then suddenly they will break. That's what happens when you heat a solid and it becomes a liquid. Whether it's ice at a very low temperature, that will happen, or the steel down in the steel mill. You heat it up and now everything has disappeared. I don't know what's going on now. Zoom is having difficulty today. Someone say something. Can you hear me? I'm guessing we got disconnected because it says my Zoom is trying to connect. Okay. We did have a pretty bad storm here. I mean, windy, and I wonder if that's knocked out communications. as in okay. My camera's off. Pretty sure I'm talking to nobody. Ah, my internet. No internet access. This is not good. All right, here's something. Okay, are y'all still there? Okay, I'm trying to get back in. Zoom is screwed up. I don't know what's happened to them, but it's screwed up. Sorry, folks. We're still recording, so if nothing else, I'll just start continuing with class just in recording. But I hate to do that with y'all sitting there waiting. Okay, folks, can you hear me? So frustrating. Okay, let's see what we can do. Okay, I'm trying to connect again. Hey, there you are. All right, we've got David has joined us. I'm sorry, Devlin. Devin, I can't read. We still have not got Mika. Has anyone seen Mika since we started? Okay. Hey, everything seems to be much better now. Okay. I don't know what happened. I do know that my internet screwed up, and so I went to a different internet source. We have a tree here, trying to get one that works well, and I couldn't get to connect even though it's a much stronger signal on the second one. But finally, the first one came back, so I went back to that. So I'm glad y'all are still here. Let me see if I can get our screen share set up again. Okay, I think that is where we were. Though I think we moved past that. Yes, I'm pretty sure we did. There we go. Yeah, we were talking about this. Now I've got to get everything else moved around again. Um, okay. Okay. Now, sorry about that. Don't know what happened. But that's what happens. Atoms in a molecule, atoms in a solid, or molecules within a solid, are fixed in place and they vibrate like crazy, okay? But they're fixed in position. That's why solids have their own volume, their own shape. Everything is fixed. When you heat them up and you make those molecules vibrate more and more, finally they break away, and that's when they become a liquid. Now, a few solids will break away and go straight to a gas phase, like carbon dioxide. Y'all know what solid carbon dioxide is called? Any of you ever been to a rock concert? You know, that smoky kind of stuff they'll sometimes have there around the stage. They have dry ice there, and dry ice is going from solid carbon dioxide to gaseous carbon dioxide. But it's so cold, it makes the water vapor in the air start condensing in the little droplets, and that's what you're seeing that looks like smoke. It's actually water droplets. Okay? So that's how you go from a gas to a liquid, add energy. Then to go from a liquid to a gas, a solid to a liquid, you add energy. Liquid to a gas, guess what else you do? Add more heat or more energy. And that's what happens when you boil water. The water molecules get moving further and further apart until finally they escape and they don't have that closeness anymore. And that's when they become steam. And you see it boiling up in the water because the water molecules are separating and becoming a gas, and that's what makes the boiling, bubbling of your boiling water. And then they become gas. And then they float around. Just like I said, looking out there today, there's a lot of water vapor in the air because it's so humid. The rain we just had, not nearly as much as there is oxygen and nitrogen, but there's still a fair amount of water vapor, and it's just floating around out there. Now, if those droplets do coalesce, like you start losing energy, then they will coalesce, and overnight they may form dew. Okay, in the wintertime, that may be a frost as it goes to a solid phase. Uh, if it gets if it's really humid and the temperature drops, you'll get fogginess. Okay, and that's where the water vapor molecules are now starting to gather together and cling together as liquids, but they're still suspended in the air. And then ultimately in a cloud, the water droplets are more and more, bigger and bigger collections until they start falling, and that's what rain is. And in the wintertime, snow or hail or sleet, okay? That would be what's happening there. The one other phase of matter we haven't talked about, now let me check again with you. Can anyone hear me? I can't hear any of you. I don't know if you're saying. Okay, good. Okay, good. All right. Ever since that last loss, I'm suspicious now. Okay, how you go from the gas to the next phase? Anyone know what the next phase is called? Plasma. What a plasma is when you've added so much energy to a gas. I'm trying to get my cursor, there it is, that now the gas molecules, you've added more energy, now they start losing or gaining electrons. And once an atom or a molecule has lost or gained electrons, it's no longer a neutral atom or molecule. It's called an ion. If it gained an electron, it became a negative ion. If it lost an electron, it becomes a positive ion. Okay? And that's what you do when you go to the next phase, and that's called the plasma. Now, let's not get into too much detail on that, but plasmas are charged gases, basically. You get it by adding energy. Now, I don't know of any in the room that I'm in now, but usually when we're in a classroom on campus, I know there's usually some there in those fluorescent tubes that provide lighting. That's what provides light in fluorescent tubes. You charge those gases that are in the tubes with high amounts of potential difference, electrical potential difference, and make ions. Those ions fly from one end to the other end. Positive ions going one way, negative ions going the other way. They're flying past, and those tubes are coated on the inside with a white phosphorescent material. And when these ions go flying past, some on that material will jump up a level of the electrons. Now remember the figure, it may still be here. Okay, let's see if it is on my whiteboard. It's a pretty ugly picture. No, it isn't. I guess when we lost the load, we lost everything. But I tried to draw hydrogen and carbon atoms, and carbon had 2 electrons on the inner shell and 4 electrons in the outer shell. Okay, now if those outer shell electrons jumped up to the next shell where there weren't any electrons, but then later fell back down, they would give off what they call a photon of energy. That white phosphorescent material that's inside those tubes, when they give off, when the electrons or the ions go flying past and they pick up energy from them, they jump up in energy level. Then when the ion passes and there's no more source of energy, they fall back down. When they fall back down, that material, that's what makes it phosphorescent. It gives off light. That's 1 photon of light, and that's what's happening in a fluorescent tube. Fluorescent means giving off light. In an incandescent light bulb, like I have actually, that may be a fluorescent bulb. I can't remember what we put in this thing. That may be a fluorescent bulb in there. Maybe I do have plasma in the room with me. But in a regular incandescent light, the lamp on the dresser over here is an incandescent bulb. I don't think it's plugged in, but if it were and I were to turn it on, how that's giving off light is heating up a filament so hot that it glows. That's a heat situation, and when it gets so hot it glows, and the filament would be one that glows a fairly white light. Whereas there's not nearly as much heat in a fluorescent, because you're not having to heat anything, you're just sending ions by a phosphorescent material. They jump up an energy level and fall back down. So that's what a plasma is. Most of what we know and see and can detect in the universe is plasma, because most of the mass of our solar system is in our sun, like 700 times more mass in the sun than all the other bodies, all the planets, all the moons, all the asteroids, all the comets, everything in our solar system. The sun is more than 700 times more massive than all the rest of it put together. And in the sun, just about everything is a plasma. It's so incredibly hot that it is a plasma there. So most of what we know about the universe, the stars, the galaxies, and all like that, what we know of them mostly plasma. There's a lot of discussion these days about how much dark matter there is out there we can't detect. So that may rival the amount that's in that. So anyway, that's what solids, liquids, and gases are. So 12.2 is talking about properties of solids. Now, I think all of you do have books, don't you? If anyone doesn't have a book, please let me know. Does anyone not have a book? Okay, does that mean all of you do have a book? At least somebody say yes. Okay, good. Okay, so I assume all of you have it. If you don't, I'll be glad to write these things down. But since all of you do, let's just go over them. I'm going to mention mostly the bold typed words. In a solid, I've already used this word once, the molecules and or atoms, whichever it happens to be, whether they're elements or compounds, the cohesion is the force that holds like molecules together or like atoms together. The force of attraction between like molecules. Whereas adhesion, there's still things being grouped together, but that's the force of attraction between different or unlike molecules. Okay? Now, water coheres to each other very, very strongly. Okay? And there's a reason for that. It's called what they call hydrogen bonding. Water molecule, and if you remember back several slides earlier, and I mentioned this when we were talking about it, but let's go back to that. We'll actually go back a few slides. Well, just do it here. Whoops. Go back a few slides. There's a water molecule right there. This end of the water molecule tends to be slightly negatively charged. This end over here slightly positively charged. Because of that charge difference, then the next hydrogen wants to stick around here, the next oxygen wants to stick here, an oxygen sticking here, a hydrogen, two hydrogens sticking here. And therefore water, even though it should be a gas, it's such a light molecule, it should be a gas, they stick together. They cohere together so strongly it's a liquid at normal temperatures and pressures. Thank you very much. We wouldn't exist if that wasn't true. Okay? Adhesion, on the other hand, is the force of attraction between different or unlike molecules, and they say some common examples would be glue. Okay? Glue on wood, tape on your skin. Okay? Tar, shoe soles, things like this that are stuck together, different things being adhered to each other. That's why we call some tapes adhesive tapes, because it's adhering to different materials. Okay? Just a general word. The next characteristic of solids, or properties of solid, is tensile strength. Now, what tensile strength is of solid is a measure of its resistance to being pulled apart. Here's a pen here. I pull on the pen, it doesn't want to separate. Okay, if I were much stronger and pulling it, I might be able to actually get it to begin to separate a little bit. And when it did, it would probably get smaller in diameter because I'm pulling the molecules further apart. The likelihood of that pen, it would just break. It wouldn't be tensile. Okay. Now, the tensile strength is measured in force required to break the rod or the wire divided by the cross-sectional area of the rod or the wire. Now, the only reason I'm mentioning that is we're going to see that same concept over and over again in different contexts. This is tensile strength, force per unit area. You measure it in those quantities. They have a good picture in the book. If you got your books, look at that. Let's go to the next one, hardness. The hardness of a solid is a measure of the internal resistance of its molecules to being forced further apart or closer together. Okay? Now, let's picture a few things. I don't know if you've ever messed much with aluminum. Okay? Um, a block of aluminum, if you have a nail and ping on a block of aluminum, you're going to make a dent in it. Aluminum is a fairly soft metal. Do that to iron, more than likely you're not going to get much of a dent, a scratch, or anything like that. But if you were to get diamond and rub that against iron, you're going to make a scratch, because diamond is harder than iron. Diamond is the hardest substance, naturally occurring substance we know of. So that's hardness. Now, in soil science and other things like that, we use the Mohs hardness scale, talking about the hardness of different minerals in the soil. This is talking about the Brunel method, named after Johann Brunel, and he's mentioned here in the book. And that's measured in mass in kilograms divided by surface area, the surface area of the impression. So that's mass per unit area, whereas tensile strength was force per unit area. Similar but different quantities. Okay? That's all we need to say about hardness. They show some machines that measure hardness. Okay? That's a Brunel hardness testing machine. Okay, let's go back to ductility. Now, ductility to me should have followed tensile strength pretty strongly. Ductility is the property of a metal that enables it to be drawn in through a die to produce a wire, whereas tensile strength was the solid of a solid as a measure of resistance to being pulled apart. So those are like yin and yang, the opposite characteristics. Tensile strength is the measure of its resistance to being pulled apart. Ductility is a measure that enables it to be drawn apart. Okay? Copper is very ductile. You can make copper wires that are pretty big around, and you can make them that are incredibly tiny around. In fact, look at the copper wires in a telephone hookup someday. I mean, those are about as thin, I don't have much, but as a strand of a hair. Okay? Those are incredibly small, very ductile material, copper. Silver, on the other hand, not very ductile at all. Okay? So let's move to the next one. Malleability. Now, it reminds me a little of ductility. Ductility is the ability to be stretched into a strand or a wire or something like that, whereas malleability is the ability to be pressed into a sheet. Okay? For instance, I mentioned aluminum. What's probably in your kitchen, you have some aluminum on a roll. What do we call that? Absolutely, aluminum foil. That aluminum has been rolled into a thing as thin almost as a piece of paper. Okay? Incredibly small. So aluminum, very similar to it being nicked pretty easily, is very malleable. Gold is very malleable. So malleable, in fact, you can have what they call gold flake. Have any of you ever messed with gold flake? If you see a picture frame that looks like it's ornately carved but seems to be gold, the odds are it's not gold. Okay, very strongly the odds are it's not gold, but it probably is carved out of wood, and then someone took a gold flake, and just basically pressed on it almost with your finger, more than likely it's something a little harder than your finger, and rolled it on there, and you actually roll the flake into the grooves of the wood, and it sticks. It looks like gold, and it's really just a very, very, very thin flake of gold. That's malleability. Elasticity. I think we mentioned this briefly in the last chapter or one before, and that's when two objects collide, and if they bounce off of each other without distorting or bending or deforming one another, that's elastic. So elasticity is a measure of a deformed object's ability to return to its original shape and size once the outside forces are removed. Have any of you ever hit a baseball with a baseball bat? I'm sure some of you have. Jalen, you have? Good deal. Do you know that you deformed that ball when you did that? And not only that, you deformed the bat, maybe just a little bit. Even if it was a metal bat, you deformed it just a little bit. Have you seen pictures of that? The ball will actually flatten out and sometimes wrap around that bat. The bat, you can't see it, but it deforms a little bit. But then as soon as the swing is complete, then the ball takes off, not very far if I'm hitting it, but it returns to its original shape and the bat returns to its original shape. You can see this when a golf swing. If you've ever watched a slow motion, very slow motion thing of the head of your golf club hitting that ball, the ball literally flattens against that golf club. The golf club probably bends back ever so slightly, and then when you complete your swing, the ball returns to its shape and takes off. Mine doesn't do very well, and the club returns to its original shape. That's elasticity. The ability, the measure of a deformed object's ability to return to its original size and shape once the outside forces are removed. Now, this is probably a little easier to imagine smacking a tennis ball with a tennis racket. If you've ever seen a slow motion of that, that ball almost flattens out into a pancake. Not quite, depends on who's hitting it. Serena Williams hitting it, it flattens, okay, pretty badly. But, and actually if you look at the backside of the tennis racket, it bulges out, okay? But then as soon as the swing's complete, the tennis racket returns to its flat shape and the ball returns to its rounded shape and heads over that net with great speed that I wouldn't be able to return. Elasticity is a measure of a deformed object's ability to return to its original size and shape once the outside forces are removed. Something that's inelastic would be something like silly putty. You throw it against the wall and it sticks to the wall. It flattens out and doesn't return to its original shape. Y'all are too young to even know what silly putty is, aren't you? Never mind. Okay? But think of anything that would do that. Mud. You step on mud and it conforms to the groove in your shoe and doesn't return to its original shape. Okay? That is not elastic. That's inelastic. Okay. Now, I don't know if you've ever noticed this. Have you ever walked across what they call a swinging bridge? You know, one of these is suspended on ropes and stuff like this. When you step on it, it goes down a little bit, and when you remove your step, it goes back. Same thing with a board. If you've ever walked across a board, you know, between an opening at my parents' house back when they were alive, it was my sister's house now, to get to the storage over the stairwell, we had a board that was there from the top step over to the storage area. And you walked, it was about 6 inches or 8 inches wide, and you stepped on it. When you stepped on it, the board sagged a little in the middle, okay? But then when you stepped off of it, it came back. That's elasticity. However, you put too much weight on something like that, and if the board broke, then you've reached its elastic limit. That's when something gets permanently deformed. Hopefully you've never been in an automobile accident, but if you have, if you've had even a little fender bender, that's why they call it that. The metal on your car bends and doesn't come back to its original shape. Okay? That's non-elastic behavior. You pass the elastic limit of that metal on your car. Now, let's go down to an example in the book. That's this one. I bet you that you have played around at least with a slinky. Are any of you old enough to know what a slinky is? It looks like a spring. Okay, exactly. And a slinky, that it will, when you put it down, go back to its original shape. But picture that a little stronger, like the coil spring in your car. You sit in the car and you don't notice it, but you stretch that spring just a little bit. Okay? You put a heavy weight on the back of a pickup truck, you're going to make the springs stretch or compress a little bit further, or stretch depending on which way it is. So if this was a spring, now this looks just like the spring on our garage door opener down in the garage, right over there, okay? When that is opening up, the spring is pulled apart and those rings look more like this. But then when you go to raise it back up, then it pulls it back up and the spring goes there. That's the spring before stretching. That's the spring being stretched. And unfortunately, we had one that reached its elastic limit. The metal got old and we did the garage door up or down. I don't remember which way it was. Suddenly, pop, and the door fell, stuff like this. The spring had let go. It had actually broken. And this goes back to ductility, I think. When you're stretching it beyond the elastic limit, it springs the spring, it doesn't come back. Okay? If you think of something like elastic band, like a rubber band, you can play with a rubber band and most of the time it's going to go back to its original strength. But if you keep fiddling with it and keep fiddling with it, at some point it gets stretched and doesn't come back. That would be stretched beyond its elastic limit. When you release it, it doesn't go back into the original form. Now it's sprung is what we call it. Okay? Beyond the elastic limit. But if you keep stretching it beyond that, you go much past the elastic limit, and this is called the fracture limit because the spring, the metal actually splits apart there. And that's what happened in our garage door. It didn't just spring like this, it actually broke and the two pieces went back because that metal right there at that place was the weakest link and it went back. Okay, and again, how do you measure this? The force that you exert on it, that's a force. How much you stretch it over the area which it's applied, the stress is equal to applied force divided by the area. Force per unit area. Okay? Force per unit area. We saw that in tensile strength. That's how we measured it. We see it again here. Force per unit area. That would be how you measure elasticity as well. Stress is equal to force per unit area. Now, that concept, let's go back to our whiteboard here, and that concept is, I'll write it down here. Stress, that's how we measure this, I'll just leave it like that, is equal to force per unit area. Force per unit area. Now, in the SI system, System International, that's the metric type system, the force is measured in newtons and area is measured in square meters. Now, a square meter is a huge area. A newton is not a very big force. And that newton per square meter has been given a name after the physicists who did a lot of study about it, and it's named a Pascal. And they already had capital P standing for something else, so they named the Pascal a PA. Now, a Pascal is a tiny tiny amount of stress, okay? Because a Newton's a small unit and a square meter is a huge area, okay? In fact, if you picture a door, a pretty wide door about a meter across, wider across than a yard, and that doorknob is just about a meter across, above the floor, so the whole area underneath that door would be 1 square meter. A Newton, that would be probably at least the force of a Newton. Am I just pushing against my hand? Very small force over a very large area is going to give you a tiny number. So that's a Pascal. If I were to open that door right now, that would increase the pressure in the room by a few pascals. You would never notice it. I wouldn't feel my ears popping, nowhere close. You would never sense that change of pressure. Okay? However, and it's called pressure, also stress, so I'm using those words interchangeably. Since it's such a small unit, we quite often measure things in kilopascals. Okay, have any of you ever seen that unit written down anywhere? Have any of you ever checked the tire pressure in your car tires, or wheelbarrow tires, or any kind of tires? If you look at the sidewalls of the tire, nowadays it'll usually give that recommended pressure in kilopascals or PSI. What in the world is a PSI? A PSI, I can't write very well. A PSI is a pound per square inch. Just like this is a Newton, that's a measure of force, divided by an area, square meter. A pound is a measure of force. By the way, a pound is much bigger than a Newton, but a square inch is tiny compared to, whoops, here comes somebody. I can't see who it is. Can you see who that is? Devin. Oh, Devin must have had to go out, maybe lost like I did earlier and had to come back. So PSI is there's he back, is a measure of pressure or stress, pounds per square inch. That's a very large measure of pressure or stress, whereas a Pascal is a very small measure. A kPa, kilopascal, would be closer to being about what a pound per square inch is, PSI. Okay, now let's go back to our screen sharing in the text. Okay, we'll go back to what was our current slide, which I can't get. There we go. There was a picture of elasticity, spring before stretching, when it's going close to the elastic limit, but if you were to release this, it goes back to its original shape. Once you stretch it this far, release it, it stays like that, beyond the elastic limit. You keep stressing, and now not only is it beyond the elastic limit, you've reached the fracture limit, and it actually breaks. Okay, that was that slide. Here is showing stress on a tabletop. These two bricks are identical bricks. They have the same dimensions, 8 centimeters by 16 centimeters by 6 centimeters, 8 centimeters by 16 centimeters by 6 centimeters, so exactly the same size. And guess what? They're exactly the same weight. They're exactly the same mass. They're exactly the same in every way conceivable. Okay? And they're both sitting on this tabletop. However, this brick is creating less of a stress on the table than this one. Why? Because the surface area over which it's acting on the table, same force, same weight, pulling down like this, gravity's pulling it downward, over a bigger surface area, 16 by 8, that's 48, no, 128 square centimeters over a bigger area. This one is doing that same over 6 by 8, which is 48 square centimeters. So the greater stress here on the tabletop from this one, lesser stress here because it's a smaller area, same weight. and stress is weight or force per unit area. Okay. Now, um, I don't know if this next slide is on here. No, it's not. Okay. If you look in your book, um, they're saying case 1 and case 2. Case 1 is the brick when the flat part of the brick is on the table. The bigger part, the 16 by 8 part, that's 128 square centimeters. The brick has a weight or force of 12 newtons downward, 12 newtons down. 12 divided by 128 is something like, oh wait, that's 128 square centimeters. You've got to get that into square meters, okay? And they show you how to do that in your book. I would do it by the train track method, but that works okay too. There's 100 centimeters in 1 meter. You square the 100, you square the 1 squared is still 1. That gives you 10,000 in your numerator there. So 12 times 10,000 divided by 128, that gives you 938 pascals. Now, it's not a lot of force, stress, okay? Not a lot of stress because a pascal is a very small unit. However, you turn the block up on edge where now it's 8 by 6, 8 this way, 6 by that way, that's only 48 square centimeters. And you do the same thing, convert that to square meters, and now you have 2,500 Pascal. 938 here, if I can get my cursor to show up again, 938 pascals here, 2,500 pascals here. Same force, brick has the same force down, gravity is the same, but the surface area is less, so you're dividing by a much smaller number than you divided by here. That gave you a stress of 2,500 pascals, or 2.50 kilopascals. This one would be 0.938 kilopascals. This is 2.5 kilopascals. So this is less than, this one's more than twice that. Okay, the stress. The forces are the same. Now the other example that I give sometime, if we were in class I'd actually be doing it with you. Let's just imagine I was dancing with my darling, okay? And she was wearing spike heels, okay? And I get my foot crossed up and get under her spike heel. Am I going to notice that? Yes, sirree, Bob, I'll notice that, okay? Because she only weighs a certain amount, her force is a certain amount, but that's a very small surface area over which is on my foot, okay? So that's going to be an enormously sharp pain where that spike heel, she steps on my foot. So let's say I was dancing with my darling, okay, same weight, same force, same everything, but this time she has on sneakers and she steps on my toe that time. It may hurt a little bit, but not nearly like that spike heel. Why? Because the heel on a sneaker is more like this, where the heel on the spike heel would be something like that. Much smaller surface area, same force, much smaller surface area than that. Therefore, you're going to have a lot more stress on my foot. I will feel that spike heel much more strongly than I will the other, even though they have the same force. Same force, but different area. Okay? They give that also in the book. The stress caused by that for the 4 square centimeter heel, that would be the tennis shoe or the flat shoe, that would be 40 pounds per square inch. 40 psi. Okay? And that 0 would be significant. Whereas when it was a 1/4 inch spike heel area, then the stress would be 640 pounds per square inch, 640 psi as opposed to 40 psi. Yes, you'll feel that a lot harder. Okay? Now, if you did the same measurement with metric units, or at least a similar measurement, here's how those relate to each other. Trying to see, yeah, it looks like they have it done about the same. The 40 psi would be on the order of 250 kPa, kilopascals. It would be 2.5 times 10 to the fifth, or 250,000 pascals, or 250 kilopascals. That would be equivalent to 40 psi. However, on the pointed heel, that would be more like 6,400 kilopascals, or 640 psi. Okay, that's approximately it. Okay, now let's move on. Now, I don't have my watch on today. My Fitbit, the battery went low and I had to put it on charge. So someone helped me keep up with time. I don't have a clock on my computer now, but I know we've been going about an hour and 12 minutes, but we had that dead time in there. So let me know when we get there. Okay, another property of solids is tension. And what tension is a stress, force per unit area, caused by two forces acting directly opposite each other. Picture tug of war. That's the picture they show in the book. Two forces directly opposite each other, that creates a tension. On the other hand, a compression, or when two forces are directly opposite each other but pushing toward each other, that would be a compression. Okay? Now, a compression would be related to what we talked about earlier of hardness, you might say, tensile strength, you might say, something like that. They're related to each other. Now, here is the illustration of a compressive force. Here we have a concrete pillar sitting there, and then the road beds up above it. Okay? The forces are compressing. This road is compressing on the top of that pillar. Okay? Now, a big transfer truck rolls over right directly overhead. It's going to add to the pressure here. You want to make sure this concrete pillar has sufficient strength to support however many heavy trucks could be over it at that one time. Okay, so that's a column under the New Clark Bridge on the crossing Mississippi River. I don't know if that's in outside New Orleans or not. It may be. Okay, I've been in New Orleans, but I never noticed the name of the bridge. But they do have some pretty big bridges over the Mississippi. Okay, but that could be somewhere else as well. They don't say. Okay, but that creates compression. Now, what if the stress is not direct like that, but is sort of at an angle? Okay, that would then cause this type of a, this is a compressive stress here. The two forces are in opposite direction. The metal, the normal force upward, and the applied force downward. That's a compressive force. Okay. This would be a shear force. Okay. You press at an angle, so the two forces are going in opposite directions but separated by some distance. Okay. That would be a shearing force, one that tends to create some stressing with it. And that would be what's happening to the book here. You're shearing the book. If you're just pressing down on the book, that's compressing the book. Yeah, you might be able to push the pages closer together, but that's all. But if you press like this, where your forces are in opposite direction but separated by a distance, now you have a shearing force. Okay. Um, Now, another type of, you might say, a shear would be a twisting force. Okay, here's the example of the shearing force. The friction of the book on the table holding it in place is in this direction. Your applied force in this direction that's trying to move it there is now shearing the book, distorting its shape in that kind of directions. The reason, you have a separation distance between them. Okay. Another type of force like that is a twisting force, and this is called a torsion, not a tension but a torsion. Okay, in this case you're pulling on the wrench handle this way, twisting the bolt in that direction, whereas the friction that's down there, you can't see it here, but it's down there between the grooves of the bolt and whatever you're going into, the nut that's on the other side or whatever, that is then creating some resistance there. So your torsion is a twisting force. Now this happens more if you're trying to loosen a tightened bolt, trying to take it out of there. If you were to do that and the bolt was rusted in place, it's not in the best of shape, and you're twisting, you may actually shear it, and it actually breaks in. The twisting force of the bolt is counteracted by the force of the wood resisting the turning. This is going into wood. Usually bolts go into nuts, not into wood, but I guess it could go into wood as well. Okay, that's the twisting force, and here's the other example of that. And this symbol is the Greek letter tau, which is like our T, and I think this is a lowercase tau, and you have a twisting force in this direction resisted by the twisting force in that direction. That is the difference. The twisting force of the bolt in one direction counteracted by the force of the wood resisting the turning pressure, and that would be create that. Now, what I was describing before of walking on a plank, that is creating a bending force. Okay, that beam that he's sitting on there is bending the wood. Now, as long as he doesn't fracture the wood, if he got off, the wood hopefully is going to come back to its original shape. Okay, however, this is a bending force. Now this is made up of two kinds of forces. On the lower side of that beam you have the tensional forces pulling the wood grains further apart, whereas on the top of that board you're forcing them closer together because the bend is forcing them closer together. So that's what's happening with bending. Your forces are pulling apart on the lower part, pushing together on the upper part, and that's what creates the bending force. If you pass that board's, I guess you would call it tensile strength or elastic limit, the board breaks. When the forces pulling apart are stronger than the wood grain holding it together, then you break the board. Hopefully not while you're sitting on it. Okay. Now, that is illustrated by this. This is a piece of, I think probably styrofoam, not styrofoam, but something like that. And these gradations here are equal when it's flat, okay? But when you bend it like that, these have separated and these have gotten closer together. When you bring it back to normal shape, then those red and blue lines are equal distance apart. So you see how you've got a tensional force up here and a compressional force down here. That illustrates what they were showing here. Okay, flipped over, of course. They finally get to an actual example here. So let's do this. How are we doing on time? Anyone got the time? 26. We only got 4 minutes. Let's see if we can get example 1 done. Okay, I think I'll go to my whiteboard again, and let's clear that out of the way, and let's see if we can get example 1 done. This is on page 320. A steel column in a building has a cross-sectional area of 2,500 square centimeters. So the cross-sectional area, this is A, is equal to 2,500 to 5, my writing stinks, 0, 0. Those are zeros. They don't look like it, but let's pretend they are. This one's significant. That one's not. And oh, I didn't do that. And the eraser's not working, so I can't erase that. So sort of ignore this right here. This is the significant digits here. And this is in square centimeters. All right. We've got a problem already. This is not a SI unit. Centimeter is not a square, not a SI unit. Square centimeter is not an SI. We need to get this to an SI unit, and the SI unit will be blank, blank, equal, we do want this to be blank, square meters. Meter is your SI unit for length. Square meter would be the SI unit for area. So which unit will we put above and below? This line's for the units, that's for the numbers. Always put the units in their place. Which one goes where? The meter goes on top and the centimeter goes on the bottom. Perfect. Now let's put our numbers in place. How many meters make up a centimeter, or how many centimeters make a meter? Whoa, that's ugly. 100 centimeters. Centi means 100. Okay? Cents in a dollar. 100 cents in a dollar. So 100 centimeters in 1 meter. Okay? So, but these are squared. So you have to square your unit here. You square your unit there. You square the number here. That's easy. That's still 1. And you square this number here, and that's much bigger. That becomes 10,000. You double the number of zeros. There were 2 zeros up there. You have 4 zeros now. There is your denominator. That's how many square centimeters are in a square meter. So you got to move this decimal 4 places that way. That makes this 0.250 square meters. So that zero is not significant. It just indicates you got a decimal coming. 2, 5, and you have 3 significant digits, so you do put one of the zeros down. That's significant. 0.250 square meters. That's what that is. Okay. Supports a weight. Weight is a force. Where is my, oh, there it is. Come on back. Okay, here we go. The force due to weight. I'll put it F sub W. I don't think the book does. But F, your force is 1.5 times 10 to the 5th newtons. That's a lot of force. 1.50. That means there's 3 significant digits here. Times 10 to the 5th. That meant you would have 3 more zeros that wouldn't be significant if you wrote it out as a number. 10 to the 5th newtons. The question is, find the stress on the column. Well, you know that stress is force per unit area. That's your formula you keep running into over and over here, and that would be force sub W. I'm not going to put the sub W, it's too hard to write, per unit area. Okay? Now put your numbers in their place. That would be 1.50 times 10 to the 5th newtons. That's fine to leave it like that. I think I just as soon have written 150,000, but that's okay. 10 to the 5th newtons divided by the area, which we found to be 0.250 square meters. Now let's see if I brought my phone's here so I can do the calculation. Let's see what we've got. There's my calculator, and that's scientific notation. I'm going to have to turn it sideways. And remember how to do this? 1.5. You don't need that extra zero for the calculator's sake, but you don't put times 10. You put EE or EXP. I don't know if you can see it. There's the EE key somewhere right there, I believe it is. EE, and then all you do is 5. Okay? 1.5 EE5 divided by 0.25, and you don't need the extra 0.25. And then you press equal, and that gave you 600,000 pascals. Okay? I was looking for my stylus. Okay, crazy. 600,000 pascals. Because a pascal is a Newton per square meter. Okay. I don't like having that big a number. I want a smaller number but a bigger unit. What would that be? And by the way, that 0 is significant, but not these over here. Those 3 are, those 3 are not. So you could write that as 600, again with this 0 being significant, kilopascals, because kilo means 1,000. So instead of your comma there, put a kilo. K stands for 10 to the third kilopascals. Or you could say 6.00 times 10 to the fifth pascals. And they wrote it both ways, 6.00 times 10 to the fifth pascal, or 600 kilopascals. All right. We have just gone over. Sorry about that. 4 minutes over, but there will be no extra charge today. I'll let you skate by without it. Okay? We'll begin next time. Now, once upon a time I had a pencil here. There it is. Okay? We'll start next time with Hooke's Law, which is at the very bottom of page 320 and moves to the top of page 321. Okay. We did get one problem done. Let's see. I think you can then do maybe number 1, maybe number 3. No, wait, those are Hooke's Law. Number 1 is only just hook number 1. Okay, that's about the only one there I think you can do. Okay, so that would be the only homework assignment for tonight. But we'll move on next time. Hopefully we won't have weather situations that cause me to lose my internet, and we have that dead time in the middle. Any questions, any issues, any problems? All right, well then we'll see you on Thursday. Today was a lot of blah blah blah. Those properties are solid. Finally we got to some real exercises. Okay, so I'll stop the sharing. And are there any questions before we leave? All right. Yes. As soon as you can get it to me. Let me put it this way. Chapter 12, we've got a few more sections. Some of them are very short. I don't know that I'll finish chapter 12 on Thursday, but we'll make good progress hopefully on Thursday. I'm guessing it might be next Tuesday I'll be giving you the next test, so it's a good idea to try to get the chapter 8 test in before I give you chapter 12. So if you want to get it in by Thursday, that'll be fantastic. A couple of people I think already have submitted it, but if you need more time, take your time, get it right, and then get it to me. But try to get it in to me before we finish chapter 12. Okay? All right, good deal. Good question. Any other questions? We wound up with 6 people here. Yep, that's what it looked like. So good deal. Glad y'all made it. I'll go on and end the recording then, end the meeting, and then I'll end the recording in a few minutes. So take care. We'll see you on Thursday.